Good morning, everyone. Welcome to the 26th Pacific Asia Conference on Knowledge Discovery and Data Mining. And now we can start the tutorial too. Let's welcome the first speaker, Qian Li. Hi, good morning.
Good morning.
Please start your part. Thank you.
Thank you. Can you give me the shared permission? Okay, thank you. Yeah, good morning, everyone. Thank you for coming. My name is Qian Li. I'm the lecturer of Curtin University, Australia. And today, my tutorial is about recent advances in causality-based recommendation. So for this tutorial, there will be two parts. So I will first give the first part to describe some general information about causality learning and also its applications. And for the second part, so Xiangmeng Wang, she's from the UTS. She's also the student I worked with. She is currently the second year of PhD student. And she will give more details about the state-of-the-art causality-based recommendations systems. So yeah, let's move on to the first part. So for the first part, I will mainly cover three aspects. For the first part will be the introduction to the recommender system. And also I will give some basic information about causal learning theory to cover the basic concept and some other state-of-the-art causal learning methods in this field. And after that, I will discuss the causal learning on the recommender system. So why we need the causal learning for recommender system. But for this part, I would like to give some general information. And for the details, Xiangmeng Wang, she will cover more state-of-the-art causality-based recommendation methods. And also for his part, she will also describe some open questions and the future work. So for the recommender system, I think most of us are very familiar with this field, because for recommender system, it is a typical information filtering technique, and it can motivate the system to recommend some items that the users might be interested. So that means for the recommender system, it can filter some important information for the users. So here are a very typical process of recommender systems. I think in our life, we have, or I think the recommender system has, very popular. And for example, in the apps, you have your phone, your smartphone, and there are many recommender system apps in your phone. And so for these apps, when you click something, the apps will definitely collect some data from your behavior. So for example, if you click some items in the menu, so the apps will collect what you have clicked, and then it will store in some database things. So, and he will collect your behavior, and after that, the apps will use the database to training a recommender system. So for the training part, it will make use of the historical records of your behavior, and then based on some recommender algorithms, it will recommend you some top key items, or it will predict some ratings for the users and to predict what kind of items the users might be interested. And finally, so the users will click or not click. So this process will repeat again and again. So that means for the recommender system, it just forms a loop. So the loop between the apps and the users. So for the users, they will interact with the apps to give the apps the data, and the apps will make use of data and to improve the recommender systems and to increase the accuracy and to make more more satisfying recommended items to the users. So yeah, this is the general process for the recommender system. And based on this process for the recommender problems, it has definitely, it will have two parts, the input and output. So for the input, we usually consider there are three main aspects. The first aspect is the items. So that means the items in the apps, for example, some videos, some books, or the films in the media recommender systems. And in addition to the items, we also need to collect the interactions between the users and the item. That means if you recommend something to the users might have some feedback based on your recommendation results. So that means it will produce some user item interactions. So like the some user view history and also some other content. So the last part could be some other site information or some other site sources. For example, we have the user and some user and item features because sometimes the apps will collect some user features, and for the item features, you can access the item features in also in the apps or in some other site information like knowledge graph. So based on the input, we definitely want to output something. So for the output, we need to, for the recommender system, we need to output something. So for the output, it's mainly about the items. So we would like to recommend some items for the users, for the end users. And all these items should be filtered because in the database or in the recommender system, there's millions of items, but for the output, we just prefer to output some few items for the users that might be. So for these kind of items, we just predict these items for the users because for this item we predict that the user might be interested. So this for the figure is just a typical process of the YouTube recommender systems. So for example, we have the video database. For the video database, it has probably millions of items. And then, so for the YouTube, it just will generate some candidates, some small groups of candidates for the next step. And for how to generate the candidate set, it probably will use the user history and some context information, or called the site information. And then it will filter into hundreds of candidates for ranking. And for ranking parts, it will use other candidate resources to filter it into a few items, so like dozens of. And finally, you will present with some dozens of items instead of millions. So this is also a information filter process, because for recommender system, it just filter millions of items into the dozens of items. So after we just discussed the main information about recommender systems, so currently we know that for this field, it has attracted more attention in the past decades. And also in this field, there's a lot of related works, a lot of models for recommendation. So here I just listed three main categories, because as we might be aware that for the recommender systems, the key thing is you have to make use of the historical feedback and to predict something based on the historical feedback. So that means for the recommender models, it should be fit the models into the data. So it's still like the fitting problem. And for this kind of problem, currently there's mainly three categories. The first category is the collaborative fielding, and it is a very classical recommender systems, recommendation methods, and it's just it will use some content-based, for example, content-based recommender models. And after that, some more advanced methods are proposed, like the representation. Here I put the shallow to differentiate this presentation with the deep learning based presentation. So for the shallow representation, it mainly concludes the metric factorization or the factorization machines. The last one could be the deep learning, because for deep learning now it has applied in many tasks. So recommender system is one of the typical tasks that the deep learning can solve. So for deep representation, it will use some deep state-of-the-art deep learning methods like the GCN, GN, something like that, to predict the user's preference based on the historical feedback. So all these typical models, as I said, is the data-driven models. So that means for this kind of models, it will use the data, and after exploring the data, it will fit the data with a model. So after the fitted model, you to train a model. So the model you have trained should be the recommendation models you want. So for the data-driven models, because we have made the conclusion the recommender system is a data-driven model. So, but here there are some shortcomings for the data-driven models. So for the first shortcoming, it could be the bias. So because the user feedback is observational instead of the experimental. So that means for the data, it usually have some missing information, but for this kind of missing information, it is not missing at random. So that means there will be some potential factors to influence the missing mechanisms. So that's why we call it is observational rather than the experimental. So yes, another point is here, as I mentioned, it's for the bias, it is affected by the hidden factors. So here I can give you an example. For example, in the recommender systems, that for the whether the user is whether the user likes the item is not predicted, is not fully determined by the user's preference. It might be affected by some hidden factors like the social media. So for these kind of examples, we also have a work to try to solve the social network bias. And I think in the part 2, Xiangmeng Wang, she will give you more details about the social network confounders. So here for the first point, I would like to stress is for the bias, it is in the data, because we are using the data to train recommender system, but unfortunately the data will have some bias. So if the data has the bias, there will be some distribution shifts between the data you used for training the recommender systems, and this distribution shift will bias the recommender models, and the bias recommender models will just generate some bias output for the users, and this bias will amplify to the data. So because we know that for the recommender system is a loop, so for this kind of loop, it will amplify the bias for each round, and finally it will make the recommender systems inaccuracy. And for the second part, second problem is explainability, because we know that for the recommender system, if you just to predict something for the users, but do not give any reasons, it will lose some users' trust, and also it will reduce the user satisfactory. And in a more general way, if you can provide some reasons for the recommended results, it can help it can benefit for the decision-making problems also. So for the explainability part, in the recent years, the explainable recommender system has also attracted many attentions in the recommender systems, and there are various of explainable recommender models proposed, but most of the explainable recommender system, I mean the classical explainable recommender system, they just based on associations. So that means they might use some spurious relations, but for the spurious relations, it will lead to the bias we have mentioned here, and also for users' feedbacks. It is just because for user feedback, it entangles the user's real interest. So how you can disentangle the user's true interest from user feedback, it is also a challenging problem for the explainable recommender systems. So here, I just want to use a slide to explain more about the bias problem, because for the previous two shortcomings, the final problem could be the bias. So for the bias, because if there is a bias in the data, so the bias will make the model to be trained towards the skewed user preference. For example, if we have a true preference distributions on the test data, and we assume that for the test data we have some stable causals. So the causation means there's it is corresponding to the spurious. So I will explain these two concepts later. So here I just show you how the bias makes will train the models towards the skewed user preference. Because if we have the true preference distribution like this, but if there is bias, that means the distribution will be skewed in the training data. So that means if you use the skewed training data, you cannot train a model to fit into the true preference distribution. So that is the main problem of data-driven recommender systems. And in addition, as I discussed, because for the data-driven models, it will infer some spurious correlations. So the spurious correlations, it is not the true the causals. I mean, it is not the true causal relations. So in that case, it cannot reflect the user's true inference. That means based on the spurious correlations, the explanations you provide cannot reflect the user's true preference. So that means the models is still not is not transparent and cannot be truly interpretable. So yeah, let's after I have covered the main information about recommender system and also the data-driven shortcomings. Here, I would like to talk about the causal learning. So this is also the main focus of our tutorial. So before we talk about the causal learning, so I just give this figure to show how it different from the previous, statistic learning and analysis, data analysis. So here probably we can divide the data science into 3 steps. So it's also, I think this is also the 3 levels from lower one to the higher level. So for the first level, it could be the description level. So for example, if we just use some data analytic tools, what we can do is we can use the tools to analyze what is the information in the data. Probably you can use some visualizer tools to visualize some information in the data. So it just present the existing information we have. So here I just call this description. And on the second level, it could be the prediction. So for the prediction, it is the main focus of the statistical learning or the machine learning, because for the machine learning, we would like to predict some new things based on the information we have. So we would like to predict what will happen. So for example, if you want to apply the machine learning to some marketing application, what you want to do is, I want to predict probably how many items I will sell for the next month. So this is a prediction problems. Definitely, it will use some historical data. For example, what do you have sell in the past several months? So by using the historical data, you can apply the machine learning algorithm to predict what will happen in future. So this is for the second step. I think it is a big improvement than the first step, because we have seek some new knowledge based on the historical knowledge we have. But we would like to achieve the third level. So what is the third level about? I think the third level is a true intelligence we are expecting, because for the previous 2 things, it just can help you to, at most, to predict some new things. But the third level, the question would be more advanced. For example, it can answer what if questions. For example, so how much more items we will sell. So if we change the selling policies, for example, if we put more advertisement on the Google, so that means here, as you might be aware, that it's a little different from the part 2, because for the part 2, it just predict something based on the information you have. But for the third part, it can bring some intervention things. So the intervention means to change what you have done in your previous steps. So for this part, it will be more intelligent than the second one, because you try to intervene what you have done in the past and to try to achieve some expected outcomes by doing the intervention. So that's why I called for the third step. It could be more intelligent than the third one. So yes, this is the 3 main levels for the current data science. And here we would like to focus on the differences between causal learning and the statistical learning or the machine learning. For the causal learning here, I just give a graph like this. So for the causal models, it will use some causal reasonings to do some observations or the outcome predictions. Or for the third level, it can do some changes for what you have done to achieve the expected outcomes. And also for the statistical learning, it's different from the causal learning, because for the statistical learning, it usually relies on some probabilistic model. So the probabilistic model is usually based on some associations rather than the causality. So for the probabilistic model, it can only give you some observations of outcome. It cannot answer some interventional questions, or it cannot change what you have done to predict what happens if you changed what you have done before. So based on the differences here, we would like to use the causal learning or the causal inference to achieve the trustable explainabilities to explain the models you have built. And also we would like to use the causal inference for the decision makings, because for the causal inference, it can provide you some advice that on how you can change the intervention, how you can change the policies you have done before. For example, the selling policies to achieve the desired outcomes. For example, what should I do? What if I just change? What if I just put the more advertisement in Google? And so what happens to the sales for the last month? So for this kind of thing, it will help you to change your policy in your next month, because it gives you some interventional suggestions on how you can change your policy in future. So this will be beneficial for the decision-making applications. So I think based on the information I just talked about, we have basic idea about what is causality. So for causality, it is, I think the notion is widely appears in science or in some decision making or even in the daily life. But for the causality here, we have a key concept is the causality or the causal relationships. So as I mentioned, for the machine learning or statistical learning, it's mainly talk about correlation or association. So it's not the causality. And finally, the causal learning would like to ask the questions like, how do you, so how you can infer the cause and effect, and how you can predict the effect of the variable you are interested. So for the causal inference, yeah, as I said, it is driven by some daily life applications, and also it is now widely applied in many applications. So for the applications, we have several different fields. I think the most applied application is about the biology and genetics. And this, because in this field, there's a lot of problems that needs to be solved by the causal inference. But now for the causal inference, it has applied into some artificial intelligence and computer science, like the image processing, the objective recognition, and also in the recommender systems. So for the causal learning, there's some significant contributors. So here I just list some people who contribute to this field. So for the first people, Donald Rubin, he is the pioneer of this causal learning, and he proposed some potential outcome framework to compute the causal effect. And for the Judy Pearl, he is also a pioneer of this field, because he proposed a structural causal model and based on the Bayesian theory. So for the causal theory, because these people, they just build the causal theory, and for the causality theory, it will help you to decide some causalizations. I mean, some causalities, how you can infer the causalities from the by using your domain knowledge and also use the data. So the basis of causality theory is a causal model. So what is a causal model? The causal model could be a graph that can that describes the core relationships of the data. So yeah, here is the Judy Pearl. He won the Turing Award in 2011 because of his contributions on the causality. So if you are interested into the causality learnings, I mean the theory part, especially how it was built at the beginning, how it was built in a statistical theory. So you can read this book. So it is also a well-known book in the causality learning. So let's move to our next question. So why we need the causal learning? Probably we just have a general information based on the 3 levels I have discussed, but here I would like to give you more specific reasons why we need the causal learning. So for the causal learning here, before the causal learning, we mainly use the statistical learning or machine learning to explore the data. So there are mainly 3 problems that needs to be improved for the previous machine learning. The first one could be the generalizability. So what does it mean? So for example, for our previous machine learning algorithms, we usually assume that the data we trained, the distribution of the training data should be similar to the distribution of the test data. So that means what we have trained in a model should be in the same environment to be the same as the environment we applied in future. But in practical, it is not true, because usually we will apply the trained model to some new environment, and this new environment will lead to the distribution shift between the training data and the testing data. So that's why here for the real world, the training and the testing would be more complicated. And for the second thing could be the explainability. So for the explainability, after you predict something for the users, they might ask why you give me these results. But for most of the machine learning algorithms, they are still black box, just like the deep learning algorithm. So for the deep learning algorithm, it has achieved satisfying performance on various of tasks. But for the deep learning, for example, it can diagnose the cancer based on the images based on the images of the humans, but it cannot tell you why it is diagnosed as the cancer. But the humans, for the doctors, it can point out some potential parts. I mean, to give you some reasons on why the image indicates that you have the cancer. So that means for the explainability is still a challenging thing for the machine learning algorithm. So for the third part could be the counterfactual reasoning. So in our daily life, the humans the humans are always asking some counterfactual counterfactual questions. For example, what if I had done this? What happens to now? So all these questions are the counterfactual questions. So that means it is a part of human intelligence, because for humans, we can answer these questions. But for the machines, it cannot answer the counterfactual questions to answer what if questions. So that's why these are the 3 main reasons we need the causal learning for the data science. So what does the causal learning bring? So here is a very, I think it's a very general table. That for this table, it just gives the 3 levels as I did before. So for the first level is association. So association means what you have seen based on the data you have. So you can answer the questions like, what is it? Or so, And also the examples for in the Medicare, in the medical application could be, what does a symptom tells me about a disease? So these kinds of things are association. So for all these things, this can be answered by the machine learning algorithm. For the second part would be the intervention. So the intervention part is related to the causal learning, because it will intervene. It will do some intervention on the behavior you have done before. For example, what if I take the aspirin? So will my headache be cured? So you have applied some intervention on the choice of medicine, and you would like to know what would happen. So this kind of intervention. The third part would be the counterfactual. So for the counterfactual, it's more intelligent as I mentioned before, because it's a part of human intelligence. We can imagine, we can retrospect what happened before, and to improve our behavior in future to achieve the desired things, the desired outcomes. So. And I think these are the three levels of the data science. As I mentioned, from the level 2 to the level 3, it can only be done by using causal learning. So for the causal learning, you might have some basic ideas. So what is the goal of causal learning? It will assess, evaluate, to quantify the causal effect of some potential causes. So for example, the causes might be the choices you have done before, like, and also for this choice, we would like to know the causal effect of the choice on some outcomes. So for example, if you got headache, so you might take two potential activities. You might take some pills or not. So if you take some pills, probably you can get an outcome. And if you didn't take the pill, probably you will get a different outcome. So for the causal learning, it will affect the behavior of taking pills on the health status of the outcome. So for the causal effect, it could be if we know that the outcome of you taking pills is Y1, and if we know the outcomes of you didn't take pill is Y2. So the causal effect should be the difference between these two outcomes. So for the causal effect, a golden approach is to use random selection. So based on a population, you just ideally divide it into two groups, and you do some experimental study to apply the treatment 1 to group 1. And also it will get some results, and then you apply the controlled a different intervention on the group 2, and you compare the difference between these two groups. And for the causal effect, there's some two levels of evaluation. The first one is individual level. So the individual level, it's about how we can evaluate some individual treatment effect. So treatment effect means the causal effect on the outcome. So for example, we have this instance U. So the individual treatment effect, just like the example for the headache, it's the difference between whether you take the pill or not. And for the population level, we have the average treatment effect. It is the causal effect on the populational level, and it should be computed by the expectations of the individual treatment effect. So here is a simple example. So for example, we have Bob, and the Bob may have two potential treatments. The treatment here we just define as whether he drinks milk or not, and also we would like to know the outcomes, whether he will sleep at will asleep at 5 a.m. or not. So based on this concept, we can define the choral effect of milk. I mean, this is the individual choral effect. It could be the difference between these two outcomes. And also we can compute the average treatment effect. But here you might notice that for the treatment here, if the Bob has drink the milk, we can never know what happened if he didn't drink the milk. So that means for the individual treatment effect, we need to know the counterfactual outcome for Bob. But for the average treatment effect, you can compute the expectations of the individual treatment effect, or you can use some other methods. So we will talk later. You don't need to infer the counterfactual outcomes. You can get the average treatment effect. I mean, you can approximate the average treatment effect. So for the causal learning, we have a basic information about the causal effect, how to compute the causal effect. But the things is not so easy because there's some fundamental problem. So here, for example, we have the causal correlations. So T is the treatment and Y is the outcome. So here for the treatment, it is the variable we are interested. And as I mentioned, so in the real world, we can only observe one factual outcome. So for example, if you have taken the pills and we got the observed outcomes after you taking the pills, this is the factual outcome, but you can never know if you just didn't take the pill, what is the outcome of not taking the pill. So that means for this part, it is counterfactual outcome. We can never know the counterfactual outcome in reality. So, another problem is you might know because we didn't know the counterfactual outcome, you might think that probably we can predict some outcome, counterfactual outcome. But the problem is we cannot predict we cannot directly predict the counterfactual outcome because the assignment is not random. So what does it mean? So for the single cause, if you have, this is the ideal case. So the ideal case means that whether you take the pills is random. So it's like random, the probability of 0.5. And if in this case, you can use some randomized controlled trial, or I mean, you can just change the T, because if we define the taking the pill as T, you just change the T to change the value of T from 0 to 1, you can get the counterfactual outcomes of this activity. But in practical, we only have, so for the reality, this case will be challenging because it is not single cause, because there's some common cause between the choice of taking pills and the outcomes. For example, age could be a common cause for taking which pills, and also for age, it will influence the health recovery. So that means based for the ideal case, you can use some randomized control trial to compute the two potential outcomes. But for the observational study, we usually have some common cause. So because of this common cause, we cannot directly predict the counterfactual outcome. So yeah, here is the problem we have for the common cause thing. Because for example, if age is a common cause in the medical examples, we have discussed the age will affect the recovery. I mean the health recovery. Maybe for the age, for the elderly people, it will recover very slow. But for the young people, it will recover quickly. And also for the age, it will affect the treatment choice. For example, there's there's some treatment that is not suitable for the elderly people. So that's why we said there's some common causes for in the real world. So this is it's a well-known Simpson paradox. So this table shows us a paradox that this table just tells us a claim that if there is some common cause, so we would have some spurious effect of this cause. So for example, if you look at the treatment A, you would find that for the treatment A is have some lower recovery rate than treatment B. So because here we have 87 and is 93 is lower, and this is 69, is 73. So if you look at the first two rows, you may have a conclusion that the treatment A is not effective, is not as effective as treatment B, because for treatment B it has bigger recovery rate. But if you look at the overall result, you will find a paradox, because if you look at the overall treatment, you know that for treatment A, it gets a higher recovery rate than the treatment B. So that means you get a paradox. So this paradox is caused by the spurious effect of the common cause. So that means because of the existence of the age, you might have some spurious effect on your applications. So that's why we need to alleviate such kind of problem caused by the common cause. So yeah, this is also we have talked about the randomized controlled trial, because as we discussed, if the ideal case that taking the pill is randomly, so it's not affected by anything else, so you can use some randomized controlled trial. You just randomly assign some people to take pill or not to take pill. So this is a good standard for learning to study the causal learning, but in practical it is time consuming, and if you have some ethical concerns, for example, if you especially in the medical applications, you cannot just ask someone to take some pills or not to take the pills. So this is the ideal case, but it is ideal. It is not often happens in the real world. What do we have? I mean, in the machine learning algorithms. So what do we have is the observational study. So what you have is only the data. So the data is obtained from the observational study rather than the randomized controlled trial. So that means the assignment is not random, just like the examples. The age, taking the pills is not random. It is affected by your age, because the age is, for example, the age can affect you which pills you need to take, and also how we can solve the common cause, I mean the spurious effect caused by the common cause. So here we use the causal learning. That means we can make a conclusion here. The causal learning will try to learn the causal effect in the observational study. How the causality learning for how we can learn the causality from the observational study. But here we have an important claim. So the causation is not the association. So why the causation is not association? So for example, so we have, this is a very interesting example. So so for example, in the summer is definitely very hot, and the high temperature will increase. I mean, we will have a direct causal relationship to the sales of the ice cream. So if the temperature increases, the the ice creams, I mean, the sales of ice cream will be increases as well. So these two things has some causation. And also, if for the high temperatures, it will cause the high electric bills, because, for example, you usually will open the air conditioning. So that means for the high temperature, it will definitely increase the high electrical bills. So these two things also have the causation. But if you ignore the high temperature, so in the reality, I mean, in your data, you might have some found some strong associations between the high ice cream sale and also the electrical bills. So what does it mean? So because in the data, you might find some strong associations between these two things if you didn't know there is a potential factor like the high temperatures. So that means these two things will give you some spurious relations. So if we do not have a common sense, we might connect these two things together. We might think that, oh, the high increase, the high ice cream sales will increase the high electrical bills. But in fact, we know that it is not true, because the strong associations between these two things is because of the existence of the high temperature. So that means for the high temperature, it's just like the age in our last example. It is a common cause between these two things. If there is a common cause, and if you didn't consider it, that might lead to some spurious relationships. So that's why here, if we found some strong associations, we cannot say that it is causation. So for the causal learning, here are some several concepts we have. So the treatment, you might be familiar with. For example, the treatment could be the pills you take, to which pills you take, or whether you take pills or not. It is a variable that to be manipulated. That means this variable we are interested in. And also for the outcome. So for the outcome, it's the variable that we want to observe. And here is the confounder. So confounder is a very important concept in causal learning. So it is in fact the common cause. So we have discussed many times the common cause before. So it has a name called confounder in causal learning. So for the confounder, it will influence both the treatment and outcome. So here is an example. So for this example, it is a very interesting example. So for example, you have the treatment here. The treatment is the variable we need to manipulate, and we would like to infer whether the treatment, for example, the reviews on some recommender systems will affect the number of customers in the restaurant. But here we have a confounder, so the common cause between these two things. Because for the common cause, it will influence the reviews on the recommender system. Also, it will affect the outcomes of the number of customers. Because, for example, for different customers, they like different types of restaurants. So in this example, it's a quite simple example to explain what are the three notions. And as we come back for the causal learning. So the problem we have is the total relation is a mixture of causal and confounding associations. Also, as here is still the example of taking pills, we have the common cause age, so it is a confounder. So what we have, it is in an observational study, and so that means, remember that we want to know the causal effect, whether it takes the pills or not. But in fact, you cannot make these equations equal because the existence of the age here, because so for the causal learning, it tries to figure out this equation, and also the inequality here, it was caused by the common cause. of this problem. So why the common cause will cause the inequality? Because the true reason is the distribution of the observed group is not representative. So what I mean is not representative. So for example, in the randomized controlled trial, if the treatment is assigned randomly, for example, you just throw a coin, and whether you take the treatment or not is 0.5. So this is the random controlled trial. But in fact, the treatment is not random. So it will usually affected by some features or by some confounders. So what you have observed is the treatment has already affected by the features. So that means it is the data you have is collected from observational study. So that means for the observed group, the observed data is not representative to the group we are interested, because there's some distribution shift due to the assignment of treatment. And also for the common cause, here is called the confounder. It will cause some problem in the counterfactual outcomes. So here we have the two probabilities. So for the treatment A, for example, if you take the treatment A, the probability looks like this. And if you take treatment B, the probability will look like this. So based on these two probabilities, the issue is that there's some covariant shift problem. So for the observed shift, because for the observed probabilities, what you have observed for the features, the features of the patient is the distribution of the patient's features you have observed is not equals to all is not equals to the features of the patients or the overall distribution. So that means for this kind of distribution, it is not a representative distribution of the overall distribution of all the patients, because what you have observed is the treatment is affected by some unknown factors. So here is the age. So it cannot be equal to the overall distributions. So it's not like the randomized controlled trial that equals 0.5. So for the observational studies, we need to learn some causal effect from the observational study, because it is not random controlled trial. So we need for the causal learning, there's three things that in the causal learning can be used for the observational study. The first one is a causal graph model, and second is potential outcome. The third one is structural equation model. So for the causal graph, if we do not consider causal learning, for the traditional machine learning, you might have some assumptions. So the assumptions about the data, but in fact, in the causal learnings, we would like to get some causal graphs. So for the causal graphs, it includes some correlations among the variables. So based on the causal graph, we can make some quantitative analysis to analyze their dependencies rather than just give some assumptions. And this is another important tool called potential outcome. So potential outcome, for example, we have the observational data. X is the features, and the W is the treatment. The T, I use T for the previous slides. So Y is the outcomes. So here, the potential outcome frameworks could be, if we assign the value 1 to treatment, we get Y1, and similarly, we can assign the value 0 to treatment, we get Y0. So these two are the two potential outcomes if you apply two different values on the treatment. So for the factual outcome, it could be one of these outcomes, so it can represent in this form. And for the causal effect, as I mentioned, it could be the expectations of the differences between you apply different treatment values. So here, how the causal inference estimate the causal effect. So remember that we are in the observational study. So we normally have some confounders that affect the treatment and the outcome. So, and it will have some confounding associations. And if we would like to transform the observational study to the random study, we need to remove the influence from the confounders to the treatment. So here there are mainly 3 steps. The first step is, to control the confounders and to adjust the confounders, and then to remove the influence from the confounders through the treatment. And also after that, you can infer the counterfactual outcome, because now the counterfactual outcome is influenced by the C and the T separately. So you can infer the counterfactual outcome. And based on the the counterfactual outcome and the factual outcome, you can compute the causal effect by just subtract these 2 things. So here are the 3 basic things so here is another information for the causal graph. So we have a causal graph like this, like the X is the cause of D and the X is cause of Y. So this is, and D has a cause, is D cause Y. So X could be the confounder and D is the treatment and Y is outcome. So based on the causal graph, you can get some structural equality. So to quantify the influence of the influence of the causality. So for example, what the D is a function of X and some other external variables. So because for the structural equations, you can just define some quantitative analysis for the causal graph. And finally, based on this causal graph, you can you would like to infer the counterfactual. So for the counterfactual, it requires strategy called intervention. So for this intervention, if you just apply the intervention for the treatment, so there's no influence between the confounder and the treatment. So that means you can just change the values of intervention to get the counterfactual outcome of the different values of D. So for the main challenges in causal inference is, as I said, there are 2: how to handle the confounders and how to deal with the treatment assignments. I mean, how to, for example, how the treatment assignment is, for example, how you the mechanism of taking pills. So how you assign the pills to the patients. And for the challenge of confounders, confounder bias is the reason for that is because of different distribution of treated and controlled group. The treated group could be the group of T = 1, and control group could be T = 0. So in the machine learning, we have some common strategies like the sample reweighting to overcome the bias problem. So for example, you can just assign some weight to each sample and to get pseudo populations to match the distributions of the treated group and control group. So if the treated group and control group, they have similar distributions, you can get the causal effect directly. So here is the counterfactual distributions, the distribution sheet for the problem, because for the counterfactual distribution is different from factual distribution because of the treatment assignment, because the treatment assignment is not equals 0.5. So this claim can be explained by these equations. For example, we have the joint distribution of X is a confounder and X is the variance or the confounders of all the of the instance, and T is the treatment. So the counterfactual the distribution of the counterfactual should be the multiplication of the distribution of covariance and the distribution, the conditional distribution here. So if you want to these two joint distribution similar, equal, so that means you have to align these two terms equal. So these terms is the treatment assignment. So that means the differences between the counterfactual distribution and factual difference is because of a difference in the treatment assignment. So if you allow these two things are the same, each of them should be equal to 0.5. So that means they are random controlled trio. So yeah, so that's why we need to pay attention to the treatment assignment. For the treatment assignment, it has also a term called probability score. The probability score is a conditional probability of assignment to a particular treatment. So given the covariance, the observed covariance. So for the probability score based method, the intuition is we want to use reweight the sample using the probability score. So for example, after we have the treated group and the untreated group. So you might see that the distributions are screwed to for the treated is screwed to young people, and for the untreated screwed to old people. So after we apply the probability score, I mean the conditional probability we have discussed, and we use that for reweighting, we can get a more balanced distributions by reweighting, for example, to reweighting the old, to give the older people more weights, and for the young people less weights. So at the level of distribution, the distribution of controlled and treated group might be matched. So if they can match, we can just compute the choral effect. So this is also another typical method for probability score based method. So it's called the doubly robust estimator. So it combines the probability score weighting and also with outcome regression. So here, because for the previous probability score based method, for the last reweighting method, it just used the probability score to reweight the samples, but here it also use the outcome, use the probability score to weight the outcome regression. So that means it's a double robust. So it applies two different strategies on both the treatment and outcome. So for the popular methods in causal learning, there are mainly four. So here I just give four types. So we have discussed the propensity score based methods. And also there's some other methods, but I would like to focus on the last one because it is the state-of-the-art methods. So it uses some representation-based methods to infer the causal effect. So for the balanced representation learning, it's a typical method for the representation-based causal learning. So the motivation is that, remember, we want to infer the counterfactual outcomes. So for the counterfactual inference, they just model them as a domain adaptation problem. For example, you have the source domain like the observed outcomes, and you have the target domain like the counterfactual outcomes. So that means based on observed outcomes, you would like to infer the counterfactual outcomes. So it's a typical domain adaptation problem. And for this paper, it just gives theoretical guarantees that though if you want to estimate the individual causal effect, so the difference between you taking pill or not taking pill, so the expected errors of such estimation is lower than these two things. So that means, so if you can minimize these two things, you can guarantee that you will get an accurate causal effect. So the first item is expected supervised learning, and the second is the distance between the learned representations. So for the first one, it's a typical thing we did for the machine learning. It's just to minimize the distance between the outcomes and to allow the model to fit into the data. But the second is a little different. So the second thing is to minimize the distance between the representation of the treated group and the control group. So this is a key contribution of this paper. It will to compute the distance. It applies some. There are some other distance metrics, MMD and Wasserstein distance. So the balance means to reduce the distance between the treated and the controlled group. So that's why it's called balancing treated and controlled group to reduce the errors. So this is the framework, and the final objective has three terms. The first one and the last one is the expected supervised learning generalization error. So for the second one, it's the distance between the learned representations. So by minimizing this loss function, they can get accurate in individual core effects, because it has proved that the errors of the individual effect is lower than these two. So, and this is another work for the balanced representation. So this work is our work we published in the transaction of neural network learning systems. So for this work, we just based on the previous work, we also model the observed space and the counterfactual space as a source and target separately, and then we can transfer the counterfactual inference as a domain adaptation problem. But for the previous work, they have some limitations, because for the model collapse, it will caused by the insufficient overlapping, and also the deep framework, because they use deep framework is model blending. So here we propose our new methods. We use the optimal transport theory, because for the optimal transport theory, it's like, for example, if you have two piles of dirt, we would like to transform the one piles to another piles using the minimum efforts. So so based on this idea, we just model the counterfactual inference as using the optimal transport. So for example, we have the factual space and the counterfactual space. For the factual space, it's just like a pile of dirt here. And for the counterfactual space, it's like the yellow dirt here. So we would like to use the optimal transport to transport from the factual, to transport some important information from factual space to the unknown counterfactual space. And by doing this, we can achieve the robustness and also some interpretability, because here you can find some match between the counterfactual and the factual space. And also based on that idea, we derive a causal optimal transport model. So for these models, we just apply the optimal transport between the propensity measures or the propensity score. The propensity measures is we define for the propensity score, for the treatment assignment. And also we design a counterfactual regularization to regularize the optimal transport. And the second contribution is we design a new proximal point algorithm to optimize this algorithm. And we also give some theoretical guarantees to guarantee that the errors of estimating Causal effect can be guaranteed by some equations. So here for the applications of causal learning, we have several toolbox for the causal inference. So here, if you are interested in the toolbox, you can find some survey, some tutorial here. So I just get some information from the tutorial. And currently, for the causal learning, a lot of researchers, they contribute to this field. They have several different toolbox, and for the supporting methods is, for example, the propensity-based method we have talked, and also some tree-based method, and and also for some other method they proposed. And here is a link. And for there's also some algorithm, I mean some code for different causal inference algorithm. So you can find more information in this survey. And here I some assumptions, but for the assumptions, I think it is not focused. It is not the key important thing for the causal learning. So I will skip the assumptions of the causal learning here. And if you are interested in the assumptions, you can ask some questions. But here it will be, I think it's out of the scope of the causal learning here. So, and for another application level, it's there's 3 different applications. For the applications, the causal learning can be applied for decision evaluation, to handle the bias, or to estimate the counterfactual outcomes. So, for example, on online advertising, you would like to know which decision you want to make to achieve the desired outcome. So, and by doing so to achieve this goal, you have to estimate the different. I mean, you have to know, you have to do some intervention on your advertising policy to see the factual outcomes or the counterfactual outcome, and then you can evaluate which policy you would like to use to achieve the desired outcome. And also for the online advertisement, so you, for example, what kind of advertising strategy you use can increase the profits of the organizations. So you want to use some effective advertising to achieve more profits. And also for the healthcare. So for the healthcare, it's a classical area that we can apply causal learning. So for example, you want to know which medicine is effective for some disease. So, and you can apply the causal learning to know whether the medicine is effective or not. So for the causal learning, because our focus is for recommendation system. So why there are some relations between the causal learning and the recommender system? So for example, in the causal inference, if you expose a user to an items, it's just like sorry, I just mixed these 2 titles. So for the causal inference, if you expose a patient to environment, to treatment, it is quite similar to expose a user to an item. So, and also you want, for the causal inference, you want to know that what would happen if a patient has received a different treatment. And for the recommender systems, you would like to know what happened if a user was recommended to a different item. So that in this example, we could see there's a close relationship between these 2 topics. And in addition, we know that for causal learning, it can solve some bias problem caused by the confounder or the common causes. So for the recommendation systems, we have different kinds of bias. For the bias, they can be modeled by the existence of the common cause. So that means we can use causal learning to solve this kind of bias. And so here there are 3 basic correlations in the recommender systems. So for example, what we prefer is the causation. So we want a pure causations. This is stable and explainable. So if the user preference has direct cause to the click, to the user behavior, but in fact, there are some confounders. So for the confounders, like the social network could be the exposure and the preference. So, and also we have some other kind of confounders. So like the correlations, the conspicuous correlations between these two things. So for example, the interest and popularity could be both affect the click behavior. So that means for the pure causation, it is we cannot get the pure causation in a recommender system. Or the more correlations we get is these two cases. So for these two cases, we have to resolve causal learning. So for the causal learning of recommendation systems, for the causal perspective, if we treat which item to view as a treatment and the outcome is user behavior, so this is the causal perspective for these two things. But as I mentioned, probably there is a common cause between these two things. But for the traditional approaches, if they just build a factorization model, so that means the A is the exposure. So if A equals 1, that means I is exposed to U. So that means the T is equals 1. And that means for the outcome, it can only estimate the observed item. So that means it cannot know the counterfactual outcomes. So that's why the causal learning is useful. For the causal learning, it can reduce the bias caused by the common cause to reduce the selection bias, popularity bias, and also because the treatment assignment is not random. So that's why we need to handle the hidden confounder, and causal learning is a good solver to handle the confounders. So the last conclusion I would like to see about the causal learning is, because for the causal learning, it tries to investigate both sides. If you have investigated both sides, you will get a more enlightened view for the things. So this is the part 1 for the general information of causal inference. And for the part 2, so Xiangmeng, she will give more details about the causality-based recommendation methods, and we mainly focus on the device and explainabilities. And we will also introduce some of state-of-the-art work and also our work. And she will also discuss some open questions and the future work. So this, this is the part 1 from me. Thank you. And any questions?
Yep.
Okay, thank you for your question. I think, how we can find the confounders. So it is a very good question, because for the confounders, let me go back to. So we know that C is the confounders, and normally, but you know, C is confounder is based on this graph, right? So this graph is the choral graph we have built. So that means if you want to know the confounders, you have to build the choral graph. So for the causal learning, there's there's also another important topic. It's called causal discovery. It can help you to discover some potential causal relationships among the variables. So that means after you build the causal relations among the group, among all the variables, you could know that which are the confounders. But that approach is complicated because, and normally it is hard to know the errors. I mean, which is a cause. Probably you can find some associations between C and T using some statistical information, but it is hard to know which is the cause, which is the outcome. So, and for the for the recommender system, usually we have to use some pre-knowledge, some domain knowledge to construct the choreograph first, rather than to do the general choral discovery, because for the choral discovery, as I explained, is in theory it is feasible, but in practical it is hard. So for the recommender systems in this field, normally you will find that if the method is causality based, they usually build a choreograph at the beginning. So for this kind of choreograph, it is built on our domain knowledge. I mean, some knowledge we have to build for the recommender systems. Okay, thank you.
Okay, thank you for speakers' great report. And if there are any other questions, you can use the chat box to ask questions or open your audio. Thank you so much. If there's no other questions, then we can continue to the second speaker.
Thank you.
Thank you so much for your report.
Thank you. So I will stop sharing.
Can you hear me? So is it any break time or just begin to the second part of the presentation?
If anyone need, maybe we can have a coffee break for 5 minutes, and then we can back later and continue the presentation.
Okay.
Thank you. Good morning, everyone. Sorry for my mistake. Our presentation will start at 10:30. And can you hear me? Let's welcome the next speaker, Xiangmeng Wang, to start her report. Thank you.
Okay. So are you able to see my screen? Yes, okay. Hello, everyone. It's Xiangmeng Wang from the University of Technology, Sydney. And today I'm going to present the second part of our tutorial, which is the causality-based recommendation method. Typically, there are some existing causality-based recommendation method, and basically, it can be divided into two main categories. The first one is the device learning-based recommendation method, and the second type is the expandability-based recommendation method. And having introduced the two main category of the causality-based recommendation method, I will then present some open questions and some future works in this topic, and followed by our referred references. So for the first type of the device learning for causality-based recommendation, there are typically two types of existing method. And the first one is the propensity score-based method, and the second one is the causal model-based recommendation-based method, including the representation-based and the counterfactual risk minimization, and also the causal intervention. And the four second types of the recommendation method, the expandable recommender based on causality, there are two types of method named the model intrinsic and the model agnostic. So I will firstly introduce the first type of the device learning recommendation method, the propensity score-based method. So the most well-known one and the most widely used one is the deconfounded recommender proposed by Wang and Liang, etc. in 2018. So the motivation of this work is that the propensity models can be trained based on either the observed ratings of the missing completely and random sample, or some externally observed user and item covariates. So in the recommendation scenario, we all know that the samples cannot be completely missing at random. So this work is basically based on the second assumption that they should be assigned some external observed user and item correlates. So the main framework of the deconfounded recommender is described in this figure. So we can see that firstly, they aims to train a exposure estimator A hat UI here by assigning some externally observed user and item covariates termed U and V, right? So by passing the externally observed user and item covariates U and V, and also the exposure here, by Poisson factorization, the final exposure variable A hat UI can be estimated by feeding the two of the user and item covariates. And based on the trend exposure estimator A hat UI, the second framework of the deconfounded recommender aims to use the trend exposure variable AUI here to outcome model based on the some conditional probability. So Here is the term a very important concept that AUI is actually a substitute confounder. So as illustrated by Qian in the first part, we can easily know that the exposure AUI is a confounder of both the D and the Y. The D here is what we call the treatment, and the Y is what we call the outcome. So we can see from this figure that the A is the common cause of the treatment D and also the outcome Y. So under such scenario, the AUI is a common, as A is a common cause, so it's essentially a confounder here. So since we have already known the exposure variable AUI from the exposure estimator, so based on the A and also the D, the final Y can be estimated through the two variable through this equation. And the third part of this model is that we should fit the outcome model by a posterior estimation. So through this equation, we can easily know that the user representation and either item representation and also some like a regulation term, the gamma and the beta can be trained from the posterior estimation. And based on this four trained variable, finally the confounded recommender can be used to predict all the potential ratings by assigning a treatment equal to 1 and estimate the outcome Y here. Right, this is called the intervention of the assign a specific value, for example, the 1 to the treatment. So the existing users for the unseen rated items can be estimated based on the four variable through this equation, and also under such scenario, the new users for unseen items can be also obtained. So basically, this works just relies solely on the observed ratings, is what we call D here. So the D is not a gold standard randomized exposure is because that this is obtained from the observed user item interaction data set. So also this work should also rely some external variable, for example, the U and the V here. So this is what we think limited the application of this work in the recommendation system. So the second category of the propensity score-based models refers to the debouncing learning and the evaluation proposed by Xiangmeng, etc. in the 2016. Actually, the debouncing learning and evaluation work is typically an empirical risk minimization framework. So in this framework, they aim to firstly estimate the propensity scores from the observational data. And so there are many existing techniques that can be used for the propensity score estimation. For example, a naive Bayes network as used in the in this people's work. So by simply learn through the naive Bayes, the propensity scores can be estimated through this equation. And also the linear regression model, for example, some linear logistic regression technique can be also applied to the propensity score estimation. So we can just easily see this is a simple form of a logistic regression. So based on the propensity scores estimated from the propensity estimation, the second part of the empirical risk minimization framework is to use the inverse of the propensity scores to reweight each sample as it comes from the golden randomized trial study. So the final learned objective can be potentially unbiased. So another contribution of this work is that they also apply the empirical risk minimization method to the recommendation system and propose a propensity score matrix factorization. Since we all know that the ERM framework selects any samples from the hypothesis space that optimize the argument of the total inverse propensity scores. So based on this assumption, they convert the EIM framework to the typical recommendation technique termed matrix factorization, and convert the term of the inverse propensity scores to the matrix factorization term by assigning the user representation Y, the user representation V and the item representation W, and also some external offset terms to the EIM framework, and get the final propensity scores matrix factorization model. So in a nutshell, this work is just doing a reweighting strategy by reweighting each sample with the inverse of the probability of receiving the treatment, such that the confounding bias of the from the confounders can be just potentially eased. And the second types of the bias learning recommendation system is what we call the causal model-based method, and the most widely used one, the representation-based, is what we care the most. So firstly, I will go to present how they can use the representation learning to the causal model-based recommendation system. So typically, this work is our first causal representation learning-based model work that published in the transaction on knowledge discovery and data. So the background of this work is what is the missing nut and the random phenomenon in the recommendation system scenario. So this is quite difficult to understand, but indeed it can bring some like external bias. So I just use a simple toy example here to address the missing nut and random phenomenon in the recommendation scenario. And as we all know that in the recommendation system, there are some like observed user item interactions. For example, the users interact with a movie here by some observed interactions. So we call this the partially observed feedback because there are some of the interactions between users and the movies are like unobserved. And the most common like leveraged assumption of the existing work, for example, the matrix factorization, may just assume that the unobserved items is missing at random. In other words, the missing of observed user item interaction is due to no reason. However, in the real world scenario, we can just think that, for example, if a user's friend tell the user, you should not to watch a specific movie, then the user has a high potential not to interact with such a movie, right? So in the real world scenario, the user item interaction is actually missing not at random. So in other words, the unobserved items follows missing at random phenomenon. And by some conventional recommendation system just take a common assumption of the missing at random phenomenon. So this will potentially bring the confounding bias to the recommendation system, and train the partially observed feedback data follows the common assumption may just terribly harm the recommendation performance. And so the motivation of this work, as I illustrated before, because we think that the social network may be a confounder that affect both the item, the movie exposure, right, and also the further observed ratings of the user. So we think the social network is essentially a confounder here that can affect both the treatment assignment and the outcome. And also this in this work, they also present an empirical study of the social network confounder. As we can observe from these two distribution map that the data in the samples in the data set follows a long tail distribution. In other words, the long tail distribution is what we call the biased distribution. And also we can observe that the user item interaction inside the social network tend to have a lot more like interactions compared with ones in the outside the social network. So based on the assumption that the social network is essentially a confounder for the treatment and the outcomes, this work is firstly design a causal graph based on some causal theory. And we can see the causal graph here is that they think the social network is a confounder that affects both the exposure and the rating here. And also the user rating can be affected by some inherent factors such as the user profile or the item profile. So by disentangling this four determinate components, this work design their model framework based on this causal graph, and the social network confounder is what we use for modeling the confounder, and the exposure model is what we use to model the exposure mechanism. And based on the social network confounder model and the exposure model, this work also design a deconfounder model based on some inherent factors that can potentially net the learned representation independent of the exposure and also the social network confounder here. And using the learned representation of the user's item and items attributed from the deconfounder model here, this work can get a final unbiased rating prediction model as denoted in this component. So typically the framework of this work contains 4 steps. Firstly, they should quantify the social confounders with some social with some mature social network embedding model. For example, this work used the node to wake here. And secondly, it should build the exposure mechanism with the exposure model, and then based on the social network confounder and also the exposure mechanism, they go to learn the balanced representation independent of the exposure with their developed the confounder model, and finally with the learned balanced representation of the users and items. Finally, these representations are leveraged for the final rating prediction. And we can see the recommendation performance of the proposed model in this paper, that the proposed model can consistently yield the best performance among all methods on the considered 5 data sets, and also compare with the SOTA causal model is what they is what we call the confounded recommender, as illustrated in the last slides. The proposed model of this work can also outperform it by a large margin. So we can just conclude that to some extent, the causal representation-based method can just outperform the ones of the propensity score-based methods, right? So the second types of the causal model-based recommendation method falls to the counterfactual risk minimization. So in this part, I should mainly talk about the recent advance in the counterfactual risk minimization works is what.
已经有人在里面了。
So jumping from the as I illustrated in the last slide, I was mainly talking about the conventional recommendation models. For example, the matrix factorization or some like causal representation learning based models. Actually, they are basically using some like historical user item interaction. However, the recent ones jump from the conventional recommendation, such as the matrix factorization, to the recommendation as policy. So this might be a little bit hard to understand why the recommendation can be termed as a policy, because a policy is just like a term in the reinforcement learning domain. Just take this picture as an example. By given some user context, we call the user rating and user behavior, some user queries and restriction of attributes as a context here, and to a recommendation agent. we can just optimally learn a recommendation policy and follows this policy. The recommendation agent can play some specific action, is what we call items to the user, and then the user gives some real-time feedback to these actions, and then use this user feedback. We can just interactively update the recommendation policy. So the compared with the conventional recommendation methods, for example, the matrix factorization, the recommendation as policy approach aims to obtain an optimal policy for recommendation task based on the real-time user feedback and the A/B test evaluation. So under such scenario, the real-time user feedback and also the A/B test evaluation is especially essential for it, because the real-time user feedback can just naturally catches the dynamic user preference on items. And also we all know that the A/B test is unbiased evaluation sitting in the causality learning theory. So naturally, the recommendation as a policy approach can achieve unbiased optimization of the recommendation task. So the advantage of it is just like unlike the conventional recommendation, the recommendation as policy can achieve the unbiased recommendation directly with the positive A/B tests. So I will mainly talk about the one work that uses the counterfactual risk minimization by using the recommendation as a policy approach. And this work is published in the Web Conference 2021. So also we can visit some like a specific advertisement of the recommendation as policy approach. However, the limitations of the online policy learning is also severe. The most crucial one is that the online policy learning can be sometimes risky and expensive, especially in the recommendation system domain. Because we can just consider a situation that if we just post some untested actions to users, then we want to acquire the real-time user feedback to such an action. So under such scenario, the untested actions can terribly harm the user satisfaction. And also, if you just casually post some untested actions, it can terribly harm the revenue of the content provider. So we might think that the online policy learning is risky and expensive. So this work just converts the online policy learning to a specific task of the reinforcement learning, which we call it the all policy learning. And this is an offline version of the recommendation policy learning that can just discard the expensive online policy training. However, although the off-policy learning can just offer opportunity for the policy learning to abandon the expensive online training, the limitation of it is also severe, because in the off-policy learning, we need like extra stage to collect some offline data set. For example, in this loop, we can see that there is a previous recommender. The previous recommender follows a login policy, what we call the PAKDD, to place some specific actions, for example, the earphone here to the user, and then the user can give some real-time rewards and pass some current states to the previous recommender. Then use this offline data set. We can just learn an optimal target policy. And finally, the target policy PAKDD is used to deploy online to maximize the long-term user satisfaction. We can immediately notice that this two stage cannot be shared, and we think that the data collected by the login policy is totally different from the distribution of the actions in the target policy. The main reason is that because the because the data are collected by the previous recommenders. So that means some specific actions cannot be placed to a user, right? So the rewards for these actions can be missing, and we cannot literally learn from what we didn't know. So the motivation of this work is they want to incorporate some context information to infer the missing rewards of the missing actions. And also based on the counterfactual risk minimization, they want to develop unbiased learning objective. So in this figure, I just draw an overview of framework of how we can just use some context information in the off policy learning framework, and then finally develop some like unbiased learning objective based on the counterfactual risk minimization. So in the first part, we can immediately notice a heterogeneous information network here. By passing some context embedding layer, we can just immediately get the context of the heterogeneous information network. And also we have some specific user and actions. And by using the context here, the constraint user context and constraint action context can be learned to the final target policy learning. And during this loop, the counterfactual risk minimization is used to bound the upper bound of the policy optimization. So follows this common paradigm, this work develop their framework as shown in this figure. Typically, it contains three main components. The first one is the core alternative state action and context representation learning. And the second one is the HIN augmented policy learning through aggregating the context-aware state representation. And finally, they use the counterfactual risk minimization to correct discrepancy between the target and the logging policy. So next, I will go detailedly through each of the components by the specific equations. And for the first component, naturally, they should like do some extra representation learning to get the current user state and also actions and context representations, right? So the first component of the first step of this component is they firstly learns the state or the representation of the current state by a GRU unit. The reason why they use the GRU unit is that we think the the past user behavior follows a sequential manner. So the GRU unit can naturally catch the time series informations and the just perfectly model the current user state through the through all of the gates in the GRU unit. And the second step of the first component is the action representation by embedding lookup layer. And the second step of the first component is they should learn the context representation by a max pooling of the CNN layer. And finally, they combine these three representations in the user the state the action interaction specific context representation layer by a attention mechanism. So the first equation is they calculate the attention of the current states, the action representation, and also the context representation. And using this second second head level attention scores, they can get the final state action interaction specific context denoted as CU to A. And the second component goes to the HIN augmented policy learning. Since we have already get the context information from the first component, we can just use this context information to calculate how the context is matters in the current user state, right? So based on this computed two attention vectors, we can refine the current user state and the current action representation by multiply the attention scores to the original input of the state and action representations. And so the having learned about the refined user and action representations through the first step, in the second component, they use this refined user and action representations to learn the context-aware policy learning by concatenating each of the current user state, the current action representation, and also the context information to learn the policy pi theta. And finally, the counterfactual risk minimization optimization objective is used to balance the representation of the target policy and the logging policies through the CIPS estimator here. So the CIPS estimator is extended estimator based on the inverse propensity score. So this term, the pi theta and the pi theta distribution and the pi zero distribution is the term is what we call it the inverse propensity score. By bounding the inverse propensity score to a maximum value of C, the CIPS estimator is developed based on this equation. And by fitting the developed CIPS estimator, we can get the final unbiased risk minimization as denoted in the R pi theta here. So as for the recommendation performance of the proposed model, we can immediately notice that the proposed HIM policy can outperform all the baseline models, including the SOTA bandit, a context-based bandit learning model. And also, because we can see that all the baseline models perform worse on the sparse Douban book dataset, because the Douban book is the most sparse one among three of them. However, we can also witness a very extraordinary performance of the HIM policy. We consider the reason is that because the HIM policy incorporates some context information to in the policy learning, so it can perfectly handle the data sparsity under such scenario. And this work also incorporates like a case study of the heterogeneous information in their model. So from this table, we can see that the because this stands for the HIM policy model with the heterogeneous information, and this stands for the HIM policy models without the HIM information. We can immediately notice that the HIM policy augmented with the heterogeneous information can outperform the counterparts without the heterogeneous information, right? So, and in these four figures, they also divided the users into different groups based on the historical user item interactions. For example, the -600 user group stands for the users that interact with less than 600 items in the data set. So the different user group stands for different data sparsity. So based on this group diversion, they also draw the final recommendation performance based on the trended HIM policy model. And we can see that the HIM policy model with the heterogeneous information can always outperform the counterpart that's trend without heterogeneous information. And also, we can get a conclusion that the heterogeneous information has a critical effect on the sparse Douban book dataset, especially on this sparse Douban user group, which is the user group that has -600 interactions with the items. So there is also another work that related to the counterfactual risk minimization based method. Is a paper published in the CIR 2022. So this work also investigates the specific learning setting, the off-policy learning, as I illustrated before. So just to give a quickly review of the off-policy learning in the recommendation is that it aims to learn a new and optimal recommendation policy based on data sets consist of logged banded data without interactive access to the simulation environment, like most of the online learning of the recommendation system. However, the challenges of the recommendation of policy learning is that they usually follows a deterministic reward assumption by assuming that the user feedback is purely dependent on the given context, and at the same time independent of other factors that may influence user feedback. So this is maybe a little bit quite hard to understand. So I just give us a little toy example here. So the deterministic rewards assumption is that like follows in the most widely used policy learning recommender that the policy is trained based on only the user context. For example, the user's personal profile, such as the user gender, the user locations, etc. By using this user context, they can just immediately give the reward, give some specific actions to a user, and then you user give the real-time reward, such as click or not to the placed action, such as the advertisement here. However, in the real world scenario, there are a lot of factors that may influence the users and the user's reward to the placed action. For example, the user's social influence and also the attributes of the placed item. So in the real world scenario, the deterministic reward assumption does not hold. However, this if we want to address the a strong assumption of the deterministic reward assumption by using only the logged banded data is not enough, because the logged banded data can only provide the partial information. So in this work, we aim to use also the context information in the off-policy recommendation system to address the distribution shift from the login policy and the target policy. And there are some existing solutions that address the distribution drift of the login policy and the target policy by using some like data imputation and the inverse propensity score method. So in the first category, the data imputation method, they usually train a logic model for creating or padding values in the login dataset, such that the data in the login dataset can potentially hold the same distribution with the data in the target policy. And so in a nutshell, the data imputation model is just performing some like curve fitting exercises. So naturally, it can suffer from the inaccurate value prediction. And the second type refers to the inverse propensity scores based on off policy. And as we just illustrated before, the propensity score is estimated from the observational data set. As at the same time, using the inverse propensity, they can just reweight each sample. So that means if action holds very less user item interaction in the past observational data sets, so the propensity score of it can be also very little. And by assigning the inverse of the propensity to the real actions, the probability of this action that to be selected in the final target policy can get like less and less. So this is what we call the Porges-Power phenomenon. So in a nutshell, the existing method that addressing the distribution shift between the logging policy and the target policy, firstly, they are just perform some curve fitting exercises, and also they can just suffer from some common drawback of the causality-based model. For example, the poor gets poorer here. So in this work, they just use a meta graph to address the poor gets poorer phenomenon in the IPS of policy. So the motivation is that we can see here, if there exists the user, right? The gray zoo just stands for the past user interaction with items. For example, user has pastly interacted with item 1, 2, 3 here. However, we will never know from the existing data set about the user feedback with the item 4 and the item 5 here, because the reward of the item 4 and item 5 can never be logged in the logging policy. However, by visiting the common attributes of a user's past behavior with the real actions, we can just infer the potential user feedback to the unobserved item I4 and I5 here. So in this work, they aims to incorporate the meta graph information to potentially learn the missing reward of the missing items in the logging data set. So the framework of this work is just denoted in this figure, and naturally it contains 4 main parts. The first one is the metagraph attention network, and the second one is the state representation module, and the third one is the neighbor attentive candidate selection, and finally they use the counterfactual risk minimization to develop the unbiased of policy learning objective. So for the first metagraph attention network, naturally just the main duty of this part is that it should learn the item entity representation from the given metagraph. And typically this component is a transformer-based neural network. And we can notice that there are 3 conventional operators in the transformer architecture: the attention, the message, and also the aggregation operator, right? So the metagraph attention network is used for parameterize the item interface among the metagraph as vector representation by typically 3 operators in the transformer architecture. The attention operator aims to know the how important a target node is informative to the the attention operator is what we use to calculate the importance of the source node to the final target node, and the message operator is what we use to calculate the information being propagated to the source node to the target node. And finally, based on the attention vector and the message vector through these 2 operators, the final aggregation operator aggregates the attentive messages to learn the final item representation. And the second part of the component is the context-aware state representation learning. Since we have also learned the context-aware item representation from the first metagraph attention network, we can just simply aggregate them to the current user state to make the current user state context-aware. Right. So the third part of this framework is the neighbor attentive candidate selection. So it aims just to select some informative actions to the target policy, such that the target policy can select one from the candidates set to recommend it to the target user. So the candidate selection just here design attention mechanism to filter out the irrelevant items to improve the efficiency of the action search. The reason why they use the attention mechanism is that most existing recommendation system work that just select some candidate actions based on some greedy search method. For example, they just select the multi-hoop labels of the user node among a knowledge graph as a candidate. However, we might think that this manner is time assuming, and also you cannot improve the efficiency of the action search. So in this component, we introduce an attention mechanism based on the current user state and the item representation to calculate the importance of one item to the current user state. So based on the learned attention vector, the candidate item can be selected based on this attention scores, and also the multi-hoop connectivity of the item nodes among the meta graph. And finally, the unbiased of policy learning uses a counterfactual risk minimization based learning objective to optimize the final top K recommendation policy. And to be more specifically, in this part, they use a specific type of the optimization policy definition term. The two-stage top K recommendation policy is the which is the multiply of the two conditional probability of the first one is given the current states, how likely the item is selected from the candidate state, and the second is by given the current state and the action state, how likely action can be selected through the candidate state. So having designed the form of the target policy, and finally this work uses the counterfactual risk minimization to balance the discrepancy by using the inverse propensity of the pi theta and the pi zero in the term here. So on the recommendation performance of the proposed emergency policy model, we can just immediately know that although they have considered a lot of baselines, including the conventional HI enhanced methods and also the off-policy learning methods, and also the context enhanced reinforcement learning methods, the proposed emergency policy can also outperform them by a large margin. And we can also see that all the baselines can perform very bad in the Douban book dataset, because Douban book dataset is an extreme sparse dataset compared with moving length. However, the MG policy can outperform all the baseline models by a very large margin. So it has an improvement of about 40% compared with all the baselines. So the third type of the causal model-based method refers to the causal intervention. So basically, they are one of the our work published in the causal intervention topic is the thematic guided distinct learning for recommendation published in the PAKDD 2022. So the motivation of this work is that they want to discover the user's true interest from the biased interaction. So you may wonder, what is the user's true interest? Just to take this picture as an example, as we can see that this graph just naturally represented the user item interaction among directed bipartite graph. However, when the users may interact with the specific items through multiple user intents, for example, user interact with item 3 with the intent of the passing the time, right? So if we can just discover the user's true interest from the whole holistic user item interaction, the potential bias in the user item interactions can be potentially eased. And also, as we can notice that all the intent, such as the passing the time, the interest matching, is the like human defined user interest. So and also existing disentangled learning on this topic can only to infer like a human defined user intent. So the second motivation of this work is they want to empower the disentangled learning with also the context information. For example, if we wanted to estimate how, why the users like a specific item, the potential reason is that the user like items brand, right? So the contribution of this work is, firstly, they have introduced the disentangled learning with the context information to the recommendation system. The introduction of the context-aware disentangled learning method can firstly potentially disentangle the intent of the users. In other words, provide some expandability to the learned recommendation results. And secondly, they incorporate an external heterogeneous information network into the disentangled learning to learn the semantic aware user intent, such as the user-specific test towards item brand. And finally, they can propose a uniform learning method termed semantic aware intent learning. And the second contribution of this work is they propose a Monte Carlo age drop inference strategy based on the causal intervention theory. In the age drop inference strategy, they firstly represent each item attributes in a form of the tree, and then use the specific causal intervention technology. They can just compute the final outcome of how the attributes plays the important role to the user intent, and finally, by comparing the absolute error variation to the threshold, they can determine the importance of the attribute to the current user intent. And the implementation of this work is, first they define a score vector to explore the relationship between the intent and the interaction. And we can see the score vector here is divided into several chunks. For example, the S1 here just stands for the first user intent, and the SQ here just stands for the Q's user intent. And by using the graph disentangling layer, they can just explore the valuable information through the higher order connectivity among heterogeneous information. And by incorporating an external heterogeneous information network, they can just learn the embedding of the acquired past instance by a CNN layer. And finally, equipping the designed edge drop strategy, they can compare they can determine the importance of the item attributes by comparing the absolute and real variation after drop a specific edge. In other words, the item attributes. And the second causal intervention work is the deconfounding for elevating BIOS application. So you may be curious about what is the BIOS application. Just take this picture as an example. As we can just observe there in the past user browsing history, the action movie is count for most of the interaction data. For example, the 70% here. However, the romance movie can only account for 30% of the user browsing history. When the recommender is trained based on the unevenly distributed user interaction data, the recommender is tend to focus more on the items in the majority group. For example, since the action movie account for the 70%, the recommended trend on it can recommend more items that falls in the category of the action movie. For example, the 90% here. And also the romance movie can get a like a less chance to be recommended by the trend recommender system. And since the recommender recommend the recommendation list, the user feedback can also be collected by placing the like specific actions in the recommendation list, and this is just a form of feedback loop that may just harm the distribution of the two recommendation data set more. So based on the four illustrations, the root cause of the bias application is the unbiased distribution of the item attributes in an observed data set. And among the items with the same ratings, the one in the majority group will receive higher prediction scores. And also the items in the majority group could drive the recommendation opportunity of the items in the minority group. So this work aims to like address the bias application based on their designed causal graph. The D here stands for the user's historical distribution over item groups. And also the U here is what they use to represent a specific user. And also the I here is item representation, and M is the group level user representation. The DUMI is the common cause of the final recommendation prediction score Y. And by designing this causal graph, and each of the variables in the causal graph can be quantified and model, and finally the outcome of the which in other words the prediction score can be modeled through the conditional probability of giving the U, D, M, and I. However, as the Qian has also illustrated that the conventional conditional probability is not work to pursue a true causality. Instead, we should to ease the potential effect from the compounding bias, because we can immediately know that the D is a common cause of the both the U and the Y, and M is the immediate variable of the D and the Y. We can immediately notice that the D is the confounder here. So in order to pursue the true causality from the U to Y, we should to do the causal intervention by blocking the front door, or by blocking the backdoor path from the D to U, denoted in this picture. The backdoor adjustment is the technique that can essentially perform the due calculation to the treatment U here by blocking the path from the D to U. So finally, by doing the causal intervention through the backdoor adjustment, the true causality can be estimated from the due calculus on the treatment U and independent with some external variables, for example, the I here. So next I will go detailing through the second types of the causality-based recommendation, which what we call the explainability-based causality model. And first I will introduce some model intrinsic method. So I'm going to talk mainly about the causal disentanglement for semantic aware intent learning recommendation. So this work is typically published in the transactional knowledge discovery and engineering. And they aims to same as the four work that published in the PAKDD 2022. This work also investigates the semantic aware intent disentangled learning. So to enhance the interpretability quality, this work claimed that it is essential to capture users' pure intent independent of bias to enhance the interpretability quality. For example, as denoted in this figure, the users may interact with items through multiple intents. For example, the user may like the item because he likes the actor of this item, and also the users may like this movie because he likes the director of the movie, right? So by pursuing the latent intent of the user interaction, the interpretability of the disentangled learning can be potentially improved. However, it is not easy to directly use the past user item interactions to infer the latent user intent, such as to make our recommendation result interpretable. Under such scenario, because here we need the external item attributes, for example, the actor or director or the genre of the item here. So naturally, we need to incorporate an external semantic network, and in this work, they use the heterogeneous information network to provide the rich semantics to the user intent. However, this is not easy to just directly incorporate the heterogeneous information network. Since I have illustrated in the BIOS application work published in the KDD 2021, the heterogeneous information may present the uneven distribution of the item attributes. For example, the attribute missing percentage of the director account for 19.7% here. However, the type attributes is missing with only the percentage of 0.14. So directly incorporates the heterogeneous information network without control the bias brought by the uneven distribution of the item attributes may potentially bring some bias to the recommendation system that can terribly harm the recommendation performance. So the motivation of this work is that they should use the heterogeneous information to provide semantics to the user intent, which we call it. They want to use the heterogeneous information to provide the interpretability to the user intent. And secondly, since they have incorporate external heterogeneous information network that may bring bias to the recommendation results. So the second motivation is that they should debias the confounding bias stemmed from the heterogeneous information network to enhance the recommendation robustness of the developed recommendation model. So just the same as the previous works, they also design a SCM model by accounting for some by accounting for the external heterogeneous information. So the context representation C here is what we learned from the external heterogeneous information network, and the U here is stand for the user representation, and the E here is what we call it the semantic where intent learned from both U and C, and I is the item representation that directly affects the recommendation outcome. So through this figure, we can just immediately notice that C is the confounder that affect both the U and the E. So in this work, we incorporate also the causal intervention through the backdoor adjustment to block the backdoor path from the C to U to pursue the true causality from U to Y. Just to elaborate more on the backdoor adjustment. So the first concept related to the backdoor adjustment is the backdoor criterion. So the definition of the backdoor criterion is that a set of the variable W satisfy the backdoor criterion related to the T and Y if and only if the W blocks all the backdoor passes from T to Y, and also W does not contain any distance of the T. So the C to U, the path of the C to U satisfy the backdoor criterion. So this is a backdoor path based on the backdoor criterion. And since the C to U is the backdoor path, we can just naturally perform the backdoor adjustment by performing the do operation. So the do operator is calculated based on the true treatment U here. So by the do operates, we can just pursue the true causality of the U on I equal to blocking the path of C to U. So the framework of this work, just based on the designed causal graph, they have developed separate components that related to the different of components of the defined causal graph, the C, U, E, and also the Y. So there are typically two steps that related to this framework. Firstly, the semantic aware user intent learning that learns the semantic aware representation E with a heterogeneous information network. And also they use the backdoor adjustment through causal intervention to fine tune the learned E. In other words, the semantic aware user intent representation to ease the bias that stem from the external heterogeneous information network. So because this work just investigate two tasks of the recommendation topic, the first one is the robustness. In other words, is the developed recommendation model more robust than others or not? And the second one is the explainability. So speaking of the first experiment part, the robustness. So as we can directly see from this figure that the proposed model can just consistently yield the best performance among all the methods. And even the SOTA model that uses the causal representation based on the context information cannot outperform the developed model. So, and another observation is that the HIN-based models can achieve better performance than the conventional matrix factorization. However, the HIN-based models consider, for example, the IFBPR, the M theory considers no bias theory from the external heterogeneous information, so they cannot be outperformed the proposed model that uses the backdoor adjustment through causal intervention to debias the bias that stem from the external knowledge. So the second task is the interpretability of the proposed model. As we can see from this intent graph, the user item interaction score in different user intent can have different interaction scores. So we can just immediately infer that the user preference score can just the user preference can differ across different user intent. And secondly, the flagrant user intent learned by the proposed model are currently consistent with the high-level item semantic by further comparing the item abstract from the external textual review datasets. And the second part of the interpretability experiment goes to the visualization of the two-dimensional TSNE projection of the learned user embedding. So we can just immediately notice that the user embedding is divided into 4 clusters that is consistent with the predefined user intent number which is the intent number equal to 4. So this also demonstrates the interpretability of learned user embeddings from the developed model. So next, I will go introduce the model agnostic explainability. So typically, there are two model agnostic methods. The first one is the Prince provider side interpretability with counterfactual explanations in recommendation system. And the second one is a counterfactual explainable recommender. And for the first paper, I will introduce what is the explanation for the recommendation. The explanation for the recommendation is to help users understand why an item is recommended, so as to increase the transparency and trust and enable the better decision making of the recommendation system. And the existing solutions of the explanation generation for the recommendation is by using some heterogeneous information network. So this type of method usually aims to learn passes that connects the user with connected items, such that they can generate some explanation. For example, the user U received item I because U follows user V, who bought item J, which has the same category as I. So the drawback of the existing solution of the explanation generation for the recommendation is that there is a critical privacy concerns that discloses other users' action. For example, we can immediately notice that the reason why the user adopt with item J is because he follows other users, right? So in this work, they just present a different settings against the existing solution of the explanation generation for the recommendation, which termed as the counterfactual explanation. So the counterfactual explanation is defined as a set of minimal actions performed by the user that, if removed, change the recommendation to a different item. So based on the definition of the counterfactual explanation, the counterfactual explanation is just purely grounded in the user's own actions. In other words, it cannot disclose to other users' actions. So this is what's the provider side solution proposed by this model or this paper. So just to give a quick toy example of how the counterfactual explanation for recommendation works in the recommendation system. Suppose there is a user termed Alice, and Alice wondering why he just received the recommendation termed why he received a specific recommendation. So the Prince just generate the counterfactual explanation based on the Alice's own actions. For example, Alice bought one item, and Alice reviewed other item, and Alice reviewed some items from the dataset highly. So the counterfactual explanation can be generated under this scenario in the form that if Alice had not have done these actions, the one of the Alice's interacted item would have been replaced by the other item that never appears in the item in Alice's recommendation list. So just in a nutshell, the explanations are just grounded in the user's own actions. So, so the privacy concern of the paste-based method can be just potentially eased. And also because the definition of the counterfactual explanation, the explanations generated through the counterfactual setting can be also scrutable and actionable and concise, which means firstly the scrutable as they are derived in a counterfactual setup, and also the second one, the actionable, as they are grounded in the user's own actions, and finally concise as a minimal state changing recommendation. So the approach of this work mainly contains two main parts. Firstly, they use the PPR scores to denote the probability of the RIC item personalized for you. So the PPR is basically a very conventional method that used for visiting the user item interaction graph to determine whether the one of the item nodes can be personalized for a user. And the second, by using the PPR scores inferred from the user item interaction graph, they develop a very core function termed swap order function. The swap order function receives as input two items. First one is the RIC, and the second one is a counterfactual item RIC hat. And also a user to output the counterfactual explanation for you. So next I will in many detail to talk about how they can generate the counterfactual explanations based on the swap order function. So in this picture, the swap order function is just being divided into three steps. Firstly, by passing the original graph for example, for node 1, the node 4 has a higher PPR than the node 4. So the node 4 is the RIC item for the first original graph. So in the second step, the swap order function just casually remove some specific edges. For example, the edge N1 and 2 here and the edge N1 and 3 here. And after removing these edges, then it calculate again to determine whether the final PPR score of the RIC item and the counterfactual item is different by calculating the PPR score again. So the counterfactual explanation generated through the swap order function can potentially be in the form that if you had not visited the N1 and 2 edge here, the N4 would have been replaced by the N5. So the N5 is basically the counterfactual sample of the N4. And the second type of the model agnostic expandable recommendation is the counterfactual expandable recommendation published in the CIKM 2021. So, existing counterfactual explanation for the recommendation model are usually user-sided explanations, including the last prints. Is that they only generate the counterfactual explanations on the user side based on the user actions. For example, if the user has not visited the specific actions, then the item will not be recommended. However, all of them just ignore to account for the attribute level counterfactual explanation. The attribute level counterfactual explanation is generated through the assumption here. If an item would not have been recommended had it performed slightly worse on some aspects, then this aspect would be the reason for the model to recommend this item. So based on the attribute level counterfactual explanations, the counterfactual explanation can be generated in the form if the item had been slightly worse on some specific item aspects, then it will not be recommended. So the problem formulation of the attribute level counterfactual explanation is they want to look for the minimal change on items features such that the item will not be recommended anymore, instead of just performing the counterfactual reasoning on the user actions. So, and the approach of this work is firstly, they design the user aspect for performance metrics and and also the item aspect quality metrics from the textual reviews from the existing recommendation data set by the conditional equation here. And secondly, based on the constructed user aspect preference matrix X and the item aspects quality matrix Y, they can build the user item ranking score calculation model SIJ here. And finally, having built the black box ranking score calculation model, they can perform the counterfactual reasoning by defined two evaluation metrics. So the final constraint optimization is to minimize the two of the evaluation metrics in the equation here. And the SIJ score is acquired from the black box recommendation model built in the second step. So there are also some open questions and future works in the causality-based recommendation method. The first one is the learnable universal solution. Since we have like mentioned a lot of bias in our previous tutorial. For example, the confounding bias, the sampling bias, the popularity bias, and the exposure bias. So it will be interesting how to develop a universal solution that can account for multiple bias and their combinations. Right. So the first future direction is the dynamic bias, because in the real-time scenario, bias are usually dynamic, right, rather than static. For example, as denoted in this figure, that along with the different months, the popularity of the items is vary along with the time. So under such scenario, the popularity bias are usually dynamic rather than a statistic one. So how to online updating of the debiasing strategy is another promising topic for us to investigate. And the third future direction is how can we develop a reinforced learning based counterfactual expandable recommender. Because through the previous illustration, all of the counterfactual expandable recommendation system is mainly performing some greedy search strategy on the predefined, including the graph, the attributes, metrics. So since the reinforcement learning can just effectively replace the greedy search, so how to use the reinforcement learning framework in the task of the counterfactual explanation generation is another promising direction. And also, since the reinforcement learning can naturally catch the real-time user system interaction, in other words, the user real-time feedback. So using the reinforcement learning can also potentially let the counterfactual explanation generation catches the dynamic user preferences. So this is the third future direction that we may be interested in. In what follows, we give our referred references in this slide. So is there any, this is pretty much my presentation today. So is there any questions, please feel free to ask.
Thank you so much for your excellent report. Is there any questions? You can using the chat box or open your microphone to ask any questions or discuss with the speaker. So if there's no other questions, then we will have a lunch break from 12 to 14 o'clock. And let's see you in the afternoon in the same conference room too. Thank you so much for the speakers' excellent reports and all of the attendants' participation. And see you soon. Thank you. Thank you so much.
Thank you. See you.